Determinants are operators of matrices, and they're defined for square matrices. One requirement for the calculation of determinant of a matrix is that the matrix has to be square. Okay, so and this will be equal to a scalar or a number, but it has to have the same number of rows and columns for this operator to be defined. So the first definition we learn is perhaps the simplest one: a matrix that has 2 rows and 2 columns. Entries defined in this way. Somehow, well, not somehow, but one way of visualizing this is that you define an operation where you're kind of cross-multiplying elements on the diagonal, A and D, and then you subtract the product of elements that are off the diagonal, which are C multiplied by B. So in this illustration, we have on the diagonal elements 5 and 8, and then that product of 5 multiplied by 8 is going to lead to this number 40, whereas the numbers off the diagonal are 4 and 6, they multiply each other and they give that leads to this number 24, and then the difference 40 minus 24 is a scalar. So in general we can say that this is a scalar, is a complex number, for example, defined. So this operator determinant really is mapping a matrix here of 2 rows and 2 columns into a number, into a scalar. Here's another example with entries that are complex with non-zero imaginary parts. Now the entries on the diagonal involve on entry 1, 1 we have 5 plus 1i, on entry 2, 2 we have 8, which means that we're still doing that multiplication of entries along the diagonal, subtracting the product of entries off the diagonal, and this leads to a calculation that results on number 16 plus 14i. So let's now consider defining the operator determinant for a matrix that has n rows and n columns. So let's suppose we start with a matrix here denoted by A. It has n rows and n columns, and the entry on row I, column j is written or denoted as A sub ij. So we're going to define this quantity here denoted as the minor of the A sub ij entry. We're going to use this notation M for minor, N sub ij, and this will be defined as the determinant of the submatrix that remains after you ignore or throw out the ith row and the jth column. So what will happen is that the definition of the square matrix A, the definition of the determinant for the square matrix A will rely on the calculation of determinants of smaller matrices, or also here called sub-matrices. So this definition is recurrent. It kind of depends on computing the same quantity as being defined at a smaller scale as you consider a sub-matrix, a smaller matrix that has fewer rows and fewer columns. And pretty soon that type of relationship will lead to the calculation of the determinant of a 2 by 2. And then once that is computed, you could back calculate and then end up with the desired quantity. Another definition we need is that one of the cofactor of an entry A sub ij. The cofactor is denoted by the letter C, and this will be a multiple minus 1 to a power here I plus j. So this is either going to be -1 or +1, multiplying the minor corresponding to the ij entry of the matrix. For illustration, let's consider this matrix with 3 rows and 3 columns, And we know that to compute the cofactor in entry 1, 1, we first need to compute the minor on entry 1, 1. The minor on entry 1, 1 is something that results by basically ignoring row 1 and column 1 and then concentrating on the calculation of the determinant of the submatrix. So this, even though the origin matrix has 3 rows and 3 columns, now we'll be working with a submatrix, a 2 by 2 submatrix with 2 rows and 2 columns. So in this case, the determinant of this matrix is equal to 16, and what comes next is to multiply that by a power of -1, such that that power of -1, that exponent, is given by adding the row number and the column number. So in this case, this would lead to -1 to the power of 2, which is 1, and 1 times 16 is 16. So we would say that the cofactor for entry 1, 1 of this matrix A equals 16. Similarly, for the cofactor for entry 3, 2, it's obtained by multiplying -1 to the power 3 plus 2, -1 to the 5, times the determinant of the matrix that results by eliminating, say, row 3, column 2. So now you're considering a submatrix, 2 rows and 2 columns. The first column of that matrix is 3, 2, and the second column contains -4, 6. And this calculation leads to the number -26. In general, the determinant of an n by n matrix is defined by what can be considered a linear combination of the cofactors. You choose a row or you choose a column, and then you would expand over that row or over that column. So here, for illustration, the first expansion is occurring. See how the first index along every term of this sum, which could be considered a linear combination of the cofactors, having the entries of the matrix as coefficients in that linear combination, that is occurring over row I, and therefore the first index here is I sub 1, I2, excuse me, I say I sub 1, it really is I1, row I, column 1, row I, column 2, row I, column 3, row I, column n to the very end. When you compute that linear combination, that will give you a number, and that number will be exactly equal to the number you would obtain if you choose to expand over another row or over a column, which is precisely, this definition may seem a little unusual, but it works. This is how it's defined. You could expand over a row of your choice or a column of your choice. Usually, one would like to identify which is the row or column that has the entries of the matrix with the most zeros, and wherever there are zeros, you choose to expand there, because that would make the calculation a little easier. In this example, we may choose to expand over row 1 using coefficients 3, 1, and 0. 3 multiplies cofactor 1, 1, 1 multiplies cofactor 1, 2, and there wouldn't be a need to compute the cofactor 1, 3, C1, 3. So this calculation leads to the following. We have, remember, the cofactors involve powers of -1 and the determinant of the submatrix that's obtained after eliminating the corresponding row and column. And then this calculation, you have to be very careful, even though this is not terribly difficult definitions. The calculations, however, may be a little meticulous and in some cases tedious. Here, the fact that there are subtractions, you have to be very careful when you are multiplying by numbers that are negative, and then sometimes those products are being subtracted, and then there are powers of -1. So you have to be very cautious, and then sometimes you can choose to expand over you could choose to expand over a different column, and because by the definition you will obtain that expansion of the cofactors should lead to the same number. So in this case, the determinant of this matrix A equals -1, and if we choose to expand over, say, the second column, that calculation should lead to -1 as well. That is precisely the point that's illustrated here last. If we choose to expand again over a convenient column, it could be any column, but expanding over the column 3, which has a 0, is going to mean that we don't need to compute that cofactor, and this calculation, which has several steps not to be underestimated, this calculation would lead to obtain also that the determinant equals -1.